So here's the actual purpose of compact classes, is to help us describe this criterion for when an additive function is actually countably additive. So theorem 143, let's say you have an algebra of sets on X, and assume that you have an additive, non-negative function mu on A. So two things to pay attention to that are needed: non-negative, additive. Then suppose you have a compact class, fancy K, of subsets of X such that something that I'm going to tell you, a criterion, then if this criterion holds, then mu is countably additive. So this will be a criterion for going from additive to countably additive. And now I'll tell you the criterion. So for every element of your algebra of sets, let's call it A, and every epsilon greater than 0. So now it feels like we're doing analysis again, right? Epsilon greater than 0. Sometimes it just feels like we're doing set theory. Okay, so there should exist some K in there from our compact class, and some other set from our algebra of sets, such that two things happen. One is that K is contained in our original thing from our algebra of sets, and our new thing from our algebra of sets is contained in K. So K is like sandwiched between them. And if I take this complement, A, delete the inside, which is the region in which K is constrained, then I can apply mu to this, right? Because an algebra of sets is closed under complements. So I can apply mu to this, and that should be less than epsilon. So that's it. That's the criterion. If there exists a compact class that makes this happen, then you can deduce that mu is actually countably additive. So this is one way of showing that a known additive non-negative function is countably additive. So what is this condition saying? I'm going to refer to this a lot, so let's call it flower. So what is this condition flower saying? Well, here's some terminology. Flower says that K is an approximating class for mu. And that's the definition of approximating class, basically, is this. So the official definition is given in definition 146. But it's basically just this. K is an approximating class for mu. So the way I like to think about this condition is that it sort of says that K, fancy K, has enough sets in it that that you can, by knowing how mu operates on sets that are near to K, or the sets that K approximates, you can sort of by limits fully understand the behavior of mu. You know, I don't know if that's really a great way to think about it. I think it's the easiest to think about this condition when K is actually a subset of A. When fancy K is a subset of fancy A, then it becomes easy to describe this condition. And let's look at that after we finish the proof of this theorem. Maybe it helps to just give this some visual before we get into using it. So this condition, so let's just fix some arbitrary A, which is in the algebra of sets. So let me use green for things that are in the algebra of sets. Then no matter how small of an epsilon you pick here, there exists some blue, let's call it K, and some other green B, so that k gets stuffed between a and b, and the region here has a value of mu, which you can imagine is like area or measure or something like that, less than epsilon. So for every a, there's a b, such that there's a k that you can stuff in between, and such that the region is as small as you want. So that condition I'll refer to as flower, and this is a way of saying k is an approximating class for mu. So let's get into the proof. So our goal is to prove somehow that the existence of a compact class, the fact that it's a compact class, and the fact that it's an approximating class that this condition flower holds, somehow that should help us prove mu is countably additive. Okay, so just getting my assumptions down, suppose A is an algebra of sets on X, mu is additive and non-negative, and K is a compact class such that flower. In other words, such that K is an approximating class for mu. Now our goal, we want to prove that mu is countably additive. Now remember, there was an earlier proposition, 133, which gave us some equivalent conditions to countable additivity. And those were pretty nice. Those were equivalent conditions, unlike here, right? What we're proving here is not an equivalent condition, but a criterion. So a sufficient, but not necessarily necessary condition for countable additivity. But back in proposition 133, we had some nice equivalent conditions. One of which was proving mu is, quote, continuous at the empty set. Remember that one? So showing that if you have a family of sets, so let's just take a family of sets, an, countable family, let's say it's a sequence in the algebra of sets, then try to prove that and we should also assume they're nested and going down to the empty set. Then we should try to prove that mu of them goes to 0. That's what's meant by, quote, continuous at the empty set. So by proposition 133, that's enough to prove that mu is countably additive. So this is now our goal, prove that mu of the ANs goes to 0. Okay, so let's think about this sequence of real numbers, mu of ANs. So the ANs are like decreasing, right? Like A1, A2, A3, they're nested like this, and when you intersect all of them, you get the empty set. Let's think about this sequence of mu of ANs. It's a sequence of non-negative numbers, right? Mu is always taking non-negative values. So we always have mu of AN greater than or equal to 0. That's just always true. And it's also a decreasing sequence, right? Since like A1 contains A2, contains A3, and so on. Mu of A1 is going to be greater than or equal to mu of A2, greater than or equal to, etc. So this is a decreasing non-negative sequence. So how do I know about this decreasing? How come this inclusion becomes this? How come mu preserves order like this? How do I know this? That was proposition, okay, let me look that up. Found it. It was 139, part 1. So that proposition told us that if we have a non-negative is important again here, non-negative additive function on an algebra of sets, then when A2 is a subset of A1, mu of A2 is less than or equal to mu of A1. So the non-negativity and the additivity of mu was needed for that. Okay, so thanks to non-negativity and additivity of mu, mu of AN is a non-negative decreasing sequence. Not necessarily strictly decreasing, but decreasing. non-negative decreasing sequence. So definitely mu of an is going to converge to something, right? So it's going to converge to whatever is the infimum of the mu of an's. That's like the monotone convergence theorem, basically. So the sequence of mu an's converges to whatever is the infimum. So our goal is to just show that that infimum is 0. So we just need to show this infimum is 0, that for any epsilon greater than 0, there is some n such that if you take mu of a, that n, then that's less than epsilon. So just show that the numbers in the sequence get arbitrarily small. That's all we have to show. Okay, let's do it. So let epsilon be greater than 0. Now let's see if we can make use of what we actually have. What we have to work with here is that there's a compact class K, so we've got this compact class in hand, and it satisfies the property flower, so it's an approximating class for mu. That's what we have to work with. So let's focus on the approximating class aspect of things. Since K is an approximating class, that tells us that any time we have one of these a sub n's, something in our algebra of sets. So how about I start with a picture? Since K is an approximating class, for each one of these a sub n's, so let me just focus on a particular one in this picture, for each one of these, and for each choice of epsilon, like this one here, or any choice of epsilon for that matter, there's going to exist some other thing, like b sub n, which is in the algebra of sets, and then also something from the compact class that can get stuffed in between, such that the area or measure, whatever you want to call it, the mu here is less than epsilon, or less than whatever positive number we pick. So let's write that and see how we want to use that. So I'm just writing down what it seems we have thanks to that condition, flower. For each n, we have that an is something in the algebra of sets, right? And we know K is an approximating class for mu, right? So it satisfies flower. So there are, let's call them Bn, Kn, such that Bn is in our algebra of sets, Kn is in the compact class, and two things happen. Kn is squeezed between An and Bn, and number two, the mu of the area that Kn has been stuffed into is less than epsilon. All right, so this is what we have achieved. Except I don't have to put the epsilon that I started with here, right? I can put any positive number I want. So in the usual strategy for analysis proofs, how about we decide later what should go here? Because I'm not really doing this with the goal in mind. I'm just sort of looking at what I have. K satisfies flower, and I'm looking at just however I can use it. How can I make any use of this? I'll have to see later what particular use of this fact helps my particular goal. My goal is to show that there's some big N, so that this is true, right? So anything can go here. So let's just remember that any positive number, right? Like if you look at flower, it's for any positive number, for any epsilon greater than 0, you get this. So any positive number can go here. And I'm going to decide later what to put here. the positive number I put here can even depend on n, right? For each individual n, I get one instance of flower applying, right? For each individual n, I've got an in the algebra of sets, and so these exist. For that specific n, I can just put any positive number here depending on that n. So it can depend on n. It can depend on n even. All right, let's decide later what that should be. So let's see, how in the world can this help us? Well, one thing we haven't really used yet is the fact that K is a compact class. It's not just an approximating class for mu, so this flower condition, but K is also a compact class. So that means anytime you have an intersection of things in K being empty, a countable family of things in K being empty, then finitely many would have been enough to get the intersection to be empty. So that sounds like a promising, useful fact here. So is there an intersection of things in K being empty? Well, we do know the closest fact related to that is, I guess, that the ANs go down to the empty set, right? The intersection of the ANs is empty. And these KNs are stuffed inside the ANs. So there we have it. Let's go ahead and use that. Since Kn is a subset of AN for all natural numbers n, and ANs intersect down to the empty set, we have that the intersection of the KNs is also empty. Now, I would not say this. I would not say that, because I don't know that the KNs are nested. There's no way for me to know that the KNs are nested. The ANs are nested and the KNs are stuffed inside them, but that doesn't mean the KNs are nested, right? But what I do know about the KNs is that they intersect down to the empty set, at least, since each KN is a subset of the corresponding AN. This intersection is a subset of the intersection of the ANs, which is the empty set. And if you're a subset of the empty set, then you're the empty set. Now the fancy K is a compact class, so now we can finally use the definition of compact class back here. It means whenever you have an intersection being empty, there's some capital N such that intersection just those finitely many is enough to get the empty set. So since fancy K is a compact class, and again, there's no topology or anything with metric spaces going on here, even though the word compact is showing up. It's just this idea of compact class. Nothing necessarily to do with compact sets. Since this is a compact class, there is some big N such that if you intersect just up to big N, then you get the empty set. Now, my claim eventually is that this big N is the big N that I want to meet my goal. Remember, my goal was to show, let's do a quick recap. My goal was to show mu is countably additive. That's equivalent to showing mu is, quote, continuous at the empty set. So I took my sequence of things in the algebra of sets that goes down to the empty set, and I want to show mu of that goes to 0. Since that's a decreasing non-negative sequence, I'm basically just trying to show that the infimum of these numbers is 0 rather than being strictly greater than 0. So I just need to show that for any positive epsilon, there's a big N such that mu of an is less than epsilon. I claim that the big N that I found down there is that big N that I want. So let's see. Well, one thing to notice is that these K's intersect to the empty set, right? The BNs are stuffed inside the KNs. So since Bn is a subset of Kn for all n, if you intersect these BNs, up to that one, then that's a subset of the intersection of the kns, which is empty, so this is empty. Now I claim that it follows that A sub capital N is actually a subset of this union of A complement B's. And this will give me a useful estimate since I know that these all have mu being very small, and I can decide later how small. So let's think about this. It's basically a set theory argument. If you take something in here, so let's say I take some x in there, then can I prove that it's in here? Well, B1 up to B capital N, the intersection is empty. So there's at least one of these that x is not in, right? Whichever one x is not in, x is in the complement, the corresponding complement in this list, right? Typo here, this should have been n, sorry. So like if x is not in B sub I, there's going to be some I such that x is not in B sub I, right? Otherwise it would be in all of these and this is empty, so that would be a contradiction. So x fails to be in at least one of these for some I between 1 and n. Then x will be in A sub I delete B sub I, because it's not in B sub I, and it's in A sub I because it's in A sub n, which is a subset of all of the earlier A's, since the A's are nested, right? They're sort of decreasing sets like that. Okay, so because B1 through Bn intersect to the empty set and the A's are nested, we have this inclusion. So, and I'm going to use that same earlier proposition, the one that I used to get that the mu of ANs are decreasing. Since this is a subset of that, and mu is an additive, non-negative function on an algebra of sets, I get this. So at first I just get this, right? Let me just copy this. At first I get this inequality, but then mu is additive, right? So that tells me that if these were disjoint, then mu of the union would be the sum of the mu's. But do I know that these are actually disjoint? I mean, I don't think I do, right? Like, there could be something in A2 I don't know, let me just draw a picture to convince myself that they need not be disjoint. So here's A1 maybe, and then maybe that's B1. So then the first set is this region in between, A1 delete B1, right? Then A2 could be like this, and then B2 could be like that. Then there's this stuff in between. Okay, I don't know if this picture is helping at all, but if you just think it through, they definitely don't have to be disjoint. But anyway, it doesn't matter, because an additive function is also subadditive, and we're just going for inequalities here. So remember that condition, finite subadditivity? That tells us that even when this family is not disjoint, mu of the union is less than or equal to the sum of the mu's. So at least we get this inequality, which is all we want. So what I'm referring to here by subadditive is proposition 139. So that told us about specifically the situation with a non-negative additive function on an algebra of sets, that it's also finitely subadditive. So again, that's a point where it uses the the non-negativity of mu, non-negative and additive. Okay, great. And our goal is to show this is less than epsilon, remember? That's why we're breaking it down like this. Our goal is to show this is less than epsilon, and then we will win. So let's see. We can make all of these as small as we want, right? So here's a tempting but wrong thing to do. It's tempting to say, okay, well, if I can just say this is less than epsilon over n, since there's n terms here, then that'll do it. So I know to just put epsilon over n here, right? That's not going to work. So if you want, you can pause the video and see if you could figure out what's wrong with that argument. But if you do that, you might want to have some notes in front of you or download the board image from Gaucho Space so you can see the whole thing. Well, actually, no. If you look at the board image, then you would see the final answer. So don't do that. Anyway, so what's the problem with this? I don't mean don't download the board image. I mean don't do it if you don't want the spoiler. Okay, but here is the spoiler. So what is actually wrong with this? It does not make logical sense at this point to start talking about capital N, right? Where does capital N actually get introduced? Here. It gets introduced here. Capital N came from K's being a compact class. That's where it came from. It's the capital N that makes it so that intersecting only up to capital N gets you the empty set. Okay, but could we have introduced capital N earlier in the proof? No, absolutely not, because the capital N depends on what family of K sub n's we ended up with, right? A different family of K sub n's might make it harder to make the intersection empty, and then you might need a larger capital N. So capital N depends on the family of K sub n's, and the family of K sub n's was provided by the condition flower when we applied that condition. So the family of K sub n's comes from what we chose here. So you see the circular dependency you can end up with? Whatever number you choose here will determine what the family of K sub n's ends up being, that flower gives you. And then the family of K sub n's ends up determining what capital N ends up being. So you can't go then and put capital N in for this number. All right, so that doesn't work. I am allowed to make it depend on little n, though. What can we do? So I can make these as small as I want, but I have to do it in a way that does not depend on how many terms are in this sum, right? There are capital N terms in this sum, but I'm supposed to decide how small these are before I know how many terms are in this sum. So how can I do that in a way that ends me up with less than epsilon at the end? Well, however many terms there are in the sum, it is a finite sum. So if I can choose how small each of these is, and by the way, I control each of these independently, right? I can put whatever I put in the box here can depend on little n. So I can make this smaller than whatever I want, this smaller than whatever I want. Each term independently can be controlled. So it's going to be a finite sum. I don't know how long, but it is finite. If I can handle the infinite sum, if it were a series of all of these, then I could handle any finite sum. So if I can just control the worst case scenario, which is definitely not as bad as if it were an infinite series, then I would be able to control any of the finite situations. So a worst case scenario, yeah, so the infinite series would be something you can handle if you just take advantage of this fact, that if you just add powers of a half, then forever, then that's still finite. You get 1, right? So that's like a geometric series with the base being a half. So we all know that we get 1 when we do this. So if I just make, if I make this one less than epsilon a half epsilon, and then the next one less than a quarter epsilon, and the next one less than an eighth epsilon, and so on up to the last one, less than, I guess, 1 over 2 to the capital N epsilon, then this is, well, you can rewrite it like this: epsilon times a half plus a fourth, just doing that, which is definitely going to be less than if you took the series, right? Which is 1. So that would work as long as you made each one less than epsilon over and then progressively higher powers of 2. So now I know what to put here. Epsilon over 2 to the n. Little n, not capital N. And that does it. So you see how controlling these independently and making them get smaller and smaller at a suitable rate, like this, allows me to handle any finite sum here, even before I know, picking these numbers here, before I know how long this finite sum will be, by just going ahead and handling the infinite sum. So now we have this wonderful way to prove that an additive non-negative function on an algebra of sets is countably additive. Try to find a compact class that satisfies flower, that is an approximating class for your function mu. Okay, so from the way I'm saying that, presumably it's not so hard in practice to do that, and we'll see in some examples soon.